Well, here we are then. It hardly seems like 4 weeks since we started out on our look at the solid coding principles, but already we're at D, which stands for the dependency inversion principle. And in fact, there's not really very much to add to tell you about the dependency inversion principle because most of it has already been covered by the ideas we looked at in the first 4 principles, particularly any situation where we started using interfaces. So that was with the open-close principle and obviously enough the interface segregation principle. Once we'd introduced those interfaces, then pretty much automatically we were following the dependency inversion principle. The way the dependency inversion principle is often termed is with 2 possible phrases. One is abstractions should not depend on details, details should depend on abstractions. Which is very true, but actually I see that really as just another way of phrasing the interface segregation principle. Remember, with the interface segregation principle, we said we should design our interfaces to fulfill the needs of clients, not to present the abilities of our library. And that's really what we're saying by details should depend on abstractions. So the library implements the interface doesn't expose the library. The other way of describing the dependency inversion principle is high-level modules should not depend on low-level modules. Both should depend on abstractions. And that's the key thing. And that both is where the name of the dependency inversion principle can be a bit confusing. Let's take a look at this in a diagrammatic form. And so what I've got here is a couple of software components that I will call simply A and B. And these could be classes, or they could be assemblies within a solution or something like that. We'll see the differences between those in a bit, but essentially we're going to say there is a dependency relationship between them, and in UML we represent relationships by lines, and the arrowheads always indicate the direction of the dependency. So here we're saying A is dependent on B, and what that means is that if we make a change to B, then there is a probability that will force us to make a change to A that otherwise A would break. Whereas we can do whatever we like to A, and that's not going to force changes to B. And if we consider what sort of things A and B may be, this may make a lot of sense. So for example, if A represents our presentation layer, our graphical user interface, and B represents our business logic, then it makes reasonable sense that we don't want a simple cosmetic change to the GUI to be forcing us to change our business logic. Whereas if we change the business logic, it doesn't seem unreasonable that that is going to require a change to the GUI to represent the new logic. The other layer we might have it at, if we're thinking of the 3-tier model, is if we've got B as the business logic, we might then have C as the data access layer. And again, you tend to have a dependency looking something like that, where we say that if we change the business logic, that shouldn't force us to change the database or whatever. Whereas if we change the data structure, then probably the business logic is going to have to change. But it has to be said that those are always compromises. It's not an absolute rule that whenever we change the database structure, that should require us to change the business logic. So let's just focus actually on those two. So we've got B as our business logic and C as our data access layer. And if we talk about the dependency inversion principle, what we might think is that means we take the dependency and we invert it. So we change that to being a dependency in the other direction. So now we've got the situation where a change to our business logic would require a change to our data access. And that's certainly not what we want, but that's not actually what the dependency inversion principle is saying. What it's saying, remember, is high-level modules should not depend on low-level modules. Well, here we've actually got the low-level module, the data access, depending on the business logic. So that's completely wrong. Our earlier attempt was better, where we had, at least there, the business logic depend on the data access. But that's what the dependency inversion principle is saying we shouldn't do. High-level modules should not depend on low-level modules. Both should depend on abstractions. So that is saying we should introduce a third entity, which it's calling an abstraction, but in programming terms, we basically mean an interface. And then both of those should depend on the interface. So we can have our interface implementation looking something like that, and then our business logic layer could reference the interface. And a thing to notice about UML is when we use that big triangular arrow to represent inheritance, or in this case to represent interface implementation, the arrowhead direction is still indicating dependency. Sometimes you see diagrams, less formal diagrams, that actually have an arrow pointing from a base class to a derived class. But that's a bit misleading because a derived class is dependent on the base class or the interface. A change to the interface requires a change to the implementation, but a change to the implementation does not require a change to the interface. So that arrowhead direction is correct. And this is what we mean by the dependency inversion principle, that both of these things are dependent on this common interface. Now, of course, there are still dependencies, and that means when the interface changes, we've now actually got to change two things. We've got to change both B and C because they're both dependent on the interface. But if we also obey the interface segregation principle, that means our interface is going to be narrow and stable. And because it's stable, it's going to change very rarely, if ever. And so now we can vary both B and C, our business logic layer and our data access layer, and not have any dependency between the two. And as I mentioned, that's exactly what we've done in a lot of the examples I've shown you with the other code principles. So let's take a look at one of those actually. Let's take a look at what we had for rock, paper, scissors when we were looking at the strategy. So remember the strategy pattern we introduced when looking at the open close principle. And the idea here was we had a player playing rock, paper, scissors, and they could keep track of their score and that sort of thing. But the actual decision as to how they were going to play the game, giving rock, paper, or scissors, was managed by this strategy object that was accessed simply through an interface. So there we had our interface I RPS strategy, rock, paper, scissors strategy, and then that was implemented in a couple of ways. We had a random strategy that just gave you a random choice of rock, paper, scissors, or we had a non-repeating strategy that gave you a random choice but would never do the same thing twice. And then in our program, we simply set that up with one player with a random strategy, another player with a non-repeating strategy, and when we run this, it asks us a name, so let's just put in Harry and Sally, asks us how many rounds, and you can see it's playing the game with those various rules. So if you look back at the diagram, I've just replaced those general purpose models with the specifics here. So we've got our interface IRPS strategy, the player uses that interface, and then we've got a couple of implementations, but all the dependency is on the interface, and so that should be nice and stable. Now it's worth mentioning one other thing to do with these dependencies. That's the situation that you'll sometimes get where, again, let's just have an A, a B, and a C, but where we get cyclic or reciprocal dependencies. So here we've got C dependent on B, we've got B dependent on A, and then we've got A dependent on C. And if we've got something like this, then the distinctions between classes and assemblies become a bit more important, because if these three things are all simply classes within the same assembly, within the same project in Visual Studio, then having that kind of cyclic dependency is perfectly straightforward in a language like C#. In languages like C++, you've got to do a bit of trickery. You've got to use things like forward declarations of classes, but it's still possible. And although it's there because sometimes it can be very, very useful, it also can lead our code to get rather cluttered. If, on the other hand, we consider those things to be not classes but actual assemblies, then we discover this sort of thing is impossible. Although you could have a situation like, say, this, where C is dependent on B and B is dependent on A, and it could get quite complex, it would always have to be a hierarchical structure, not a cyclic structure. You could never get these cycles in there. And for that reason, that's another reason why it's a good idea to break down our .NET applications into a large number of small projects, because it means we are forced not to have these cyclic dependencies. As I say, occasionally they're useful, in which case put them within the same project. But if you can split things into separate projects, that will mean that you simply can't have these complicated and difficult to maintain relationships. And in fact, that's another of the small changes that I've made here when it comes to rock, paper, scissors, because you can see I've actually divided this up into 4 very, very limited, isolated projects. So we've got rock, paper, scissors basics, where we simply have the enum with the signs, and then the rules for what beats what. And then in there, I've also got the strategy interface. So that's what we've got there. I've then got a completely separate strategies library, which is where we have the two strategies we've got so far. And with that, you can see that only depends on basics. I've then got gameplay, where we have the game that just puts the two players together, runs them through their paces, and the player, which remember uses the strategy. And that, again, only depends on basics. And then finally, we've got the program, where we actually create the players and the game and put them together. And that obviously has to depend on both gameplay and strategies, but those two are independent. And because we've kept them as separate projects, as separate assemblies, there's no way that we could have a complicated cyclic dependency. And so that's just another way of making things a bit safer. Now, when we talk about dependency inversion, another concept that sounds similar and is associated is dependency injection. But they are different things. Dependency inversion is about the structure of your application, and what we've seen here, that two modules or two components should depend on an interface, not in either direction depend on each other. But you still have the issue, how you actually hook up the final configuration of all these objects. And we can see in the example here that I've not done it in a particularly clever way, because here we can see that in our program, we have to hard code in this case that player 1 is going to have a random strategy and that player 2 has a non-repeating strategy. What we'd like to do is make that something much more dynamic, so that when we add a new strategy, or if we just want to configure things differently, we can do that in a much more automatic way. Now, dependency injection, there are lots of ways of doing it. You can get third-party libraries like Castle Windsor or something like that. Or you can, in .NET Core, there is now a built-in dependency injection framework, or you can write it for yourself. And I thought I'll show you how to write one for yourself for this sort of thing. So we'll add a new project to this. So add new project. We'll go for a .NET standard library. We'll call this rock, paper, scissors .factory. And then first thing I've got to do is just change the properties of that, because all my other libraries are on standard 2.1. And then we'll change the name of this class 1 to our RPS strategy factory. The way this is going to work, we're going to go through all of the DLLs in the project and find any that contain classes that can be used as strategies. And the defining quality of that is if it's a class that implements the IRPS strategy, then it's going to be a strategy. So what we'll do here is we'll pop in a constructor. And in here, I'm going to say that my target interface is type of, and then IRPS strategy. It doesn't know what that is, so let's just let it add the reference. And so now it's happy with what we've got there. So we've added a dependency there, keep track of these, so that that is dependent on rock, paper, scissors .basics. Now then, what I'm going to do is I'm going to just look through all of the files that I've got locally. So we'll say files equals directory.get files in the current directory. So that's environment dot current directory, and then anything that matches star.dll. So I'm going to read in all of the DLLs, and then we'll say for each var DLL in files, and then for each of those I will load up the assembly. So assembly dot load from. So that will load the assembly into memory, not in the usual way of loading assemblies, which is because we've previously referenced them in Visual Studio. This is going to load it in dynamically. And then having got that, we're going to say something like var strat, or strat type, let's say, equals, and then asm.getTypes. So that gets us all of the types in the assembly. But then we say .where that particular type. Firstly, we want to check that it's not the target interface itself, because the interface is not a valid strategy. It's the interface for all the other strategies. But we do want to then check that the target interface is something that's supported by the type we're dealing with. And so all of that, I think, should give us each strategy that isn't the interface but is supported by the interface. And then what we'll do with that is just have a private list of types that we'll call underscore strategy types. And then we can simply, in here, notice this could be more than one. That's a collection of types. So we'll, on our private field, we'll do underscore strategy types dot add range. Let's just be clear about that. That's the plural. And so doing all that should work fine. So as soon as we create one of these RPS strategy factories, then it will go and load the types for everything we want. So let's make use of that straight away in our program. Let's go to the beginning of our program. And the very first thing we'll create is we're going to say var factory equals new RPS strategy factory. And then again, we're going to have to add the reference. So now the program has a reference to the factory. Next thing we're going to do then, while we're in the program, is having read in player one's name, let's ask the question, player one strategy. Which is a bit of an unfair question because we don't know what the strategies are. So what we'll do there then is we will actually give them a list of the available strategies that we can get from the factory. So we'll have factory dot, and then let's call it options. Haven't written that yet, but we'll get around to it. And then we could do something like read in player one strategy, P1 strategy. So the player can type in their strategy. Not particularly friendly. I mean, much nicer to have a drop-down list, but that's not really the focus of what we're doing here. And let's also do the same thing for player two. So having got player two's name, we can then have the player two strategy. And again, we've still got to provide this option. So let's go back and do that in the factory. Simply enough, we can have a public string options. So this is going to be a property with a getter. And we're going to have a string builder. And then we can just do something like for each for strat in and then underscore strategy types. And then Bob dot append strat dot name. So that'll be the name of the strategy. Won't be in a particularly friendly form. It'll not have spaces or anything, but it'll be good enough for now. And then also we need to comma separate that. So we're going to say if we're not at the very end, so if strat doesn't equal underscore strategy types dot last, then we'll also append comma space. And then at the end of all that, just return Bob dot toString. And we're actually at a point now where we can test that because we're already using that options. So let's run this up. Player one name. And then we can see that's working because we've got the two strategies that is dynamically selected from the library. And so if we type one of those in, not going to do anything as yet. And then we'll see the same one happening there. So up to that point, it's working. Now all we've got to do is in here, rather than hard coding those strategies, we simply want to put in here factory.create and then the name of the strategy. So P1 strategy, or in the other case, P2 strategy. And let's generate a stub for that and go there. And then this is actually very, very simple. Let's change the name there. So let's just call that name. Because what we need to do is just say var type equals, and then from our strategy types, we need to get hold of the matching type. So t gives t.name equals the name passed in. So that will give us the particular strategy type from the list. Then we can use activator, class provided for exactly this purpose, dot create instance from the type we've just selected. And the only issue with that, create instance returns an object, so we've got to cast that to our IRPS strategy. And so now that code in the program should work fine. And so now we should see when we run that up. So we'll go for Harry playing non-repeating strategy. And we'll go for Sally playing random strategy. 5 throws. And you can see it's playing. We don't need to check the strategies, but it has dynamically loaded it. We can now actually go a little bit further than that, because having done that, we actually now have no direct compile time dependencies on those strategies. So if I just open up the folder for those strategies and drill down, and I'm just going to steal the DLL for the strategies, so I'll copy that. Let's remove strategies altogether. So I'm not throwing it away entirely, but I'm removing it from the project. So we now should have no dependencies on it. I may need to make a few changes, remove that using directive, but we didn't need it because we'd removed the direct reference to the strategies anyway. So that should now build fine. Problem is, at the moment, if we run that up, we've got no strategies. So what we then need to do, having copied that DLL, we need to paste it into the runtime directory that we've got here. You could actually, for deployment, configure it to have a separate folder for this, but I'm just popping them straight in there. So if we do a paste in there, the rock, paper, scissors strategy is in there now. And so now if we run that up, you can see, because I just looked at the local folder, it found the strategies, and so that's working fine. That's removed one of our dependencies. Another one that we can remove, actually, if you look at this factory, we can actually make this even more general purpose, because it's a factory for RPS strategies, but it doesn't really have to be. What I can do is, if I just rename that strategy factory, I could make that a generic. So if I do something like give it a name interface type in there, and then everywhere that I've previously mentioned RPS strategy, so in there, and in there, and in there, we just replace that with a generic type. That means, as it's showing us by graying it out, we can get rid of the basics, and in fact we can remove the dependency on basics. This is now not dependent on anything. It's a very, very general purpose component. And then simply in our program, which of course does have to be dependent on the correct strategy type, we just now in there say IRPS strategy. We will have to add in the using for that, but that's fine. And so that now has further reduced our dependencies. So another way of reducing dependencies is to use generics, because we could see there that the factory doesn't need to have a dependency on the type it's creating. Effectively, we have injected the dependency into the factory itself. And again, just to test that that works, if we run that up, we should still see that we're getting those two strategies. And finally, the really nice thing about this, just to show you, is this is a sort of way you can then write, in this case, a games program that other people can provide features for. So if we simply published our rock, paper, scissors basics, remember that has the signs and the RPS strategy, then anybody could provide a new strategy for a new way of playing, and it could be shipped to us and delivered and installed just by popping it into the folder. So actually, here's one I prepared earlier, where we've got these bonus strategies. So if I take that and then go down into our game bin debug core, pop that in there, no rebuilds, nothing like that, just now run that up, and we'll see that now we've got 3 more strategies. This rocks, cut to the chase, and over the cracks. These are not very clever strategies. This rocks always plays rock, cut to the chase always plays scissors, over the cracks, you can understand what it's all about. But the point is, we've added them with no dependency issues at all. So if I say that Harry is going to play this rocks, whereas Sally is going to play cut to the chase, then we can see Harry always wins because rock always beats scissors. Not clever gameplay, but really nice programming in the way we've really broken down those dependencies. So we applied 2 key things here. We applied the dependency inversion principle, which meant that we had everything where possible dependent on interfaces. And then we used dependency injection. Lots of ways you could do it. I wrote it for myself here so that we can then hook up the different configurations. But really important thing to remember is dependency inversion only works if you also follow interface segregation. So because our interfaces were narrow and stable, that means they're good things to be dependent upon because they're not going to change and not going to cause us to have to change other bits of code. That's it then. Those were the 5 solid code principles: the single responsibility principle, the open-close principle, the Liskov substitution principle, the interface segregation principle, and today, the dependency inversion principle. I'm going to be doing a few follow-ups on these because some of them have raised interesting issues. Some of them I could have gone for a long, long time with lots of other things. Probably not the immediate following videos, but fairly soon. But anything you want videos on, do put in a comment in there. Do also subscribe, and I'll see you next time.